Hello Math 1100 students. Now let's begin Chapter 3. Chapter 3 of our textbook is going to be covered by Lesson 5 and 6, Functions and their Graphs 1 and 2. Previously in Chapter 2 we had been studying graphs. Now in Chapter 3 our new focus of attention is the concept of functions. But then again, what is it? What do you mean by a function? That's going to be answered in subsection 1.5 here. So for the time being, we have to do some preparations. And the first piece of preparation for that is the Cartesian product. Let's begin with a couple of non-empty sets, x and y. Capital X and capital Y, I mean. And they have to be non-empty because if you have an empty set, then there's nothing there, so we can't do anything about it. Now the Cartesian products x times y is defined by a set of all ordered pairs, small x, small y, where small x and small y are elements of capital X and capital Y respectively. Like this. A simple and elegant formulation that includes everything. But then again, it's too abstract. So let's go over to a couple of examples to help you out your understanding. And here's the first example. Let's consider x and y given by two finite sets, 1, 2, 3, and AB. In that case, the Cartesian product x times y is the set of all ordered pairs, 1a, 1b, 2a, 2b, 3a, 3b. There are 6 elements, 3 times 2. In general, if you have m elements and n elements together, then the Cartesian product will have to have m times n elements. That's always the case for all finite sets. Now, what if we have infinite sets flying around? Here's the most important example for our purpose. When x and y are both set of all real numbers, in that case, x times y is r times r. So we have r2 given by the ordered pair of real numbers x, y. Now, what kind of set is this? It is called a coordinate plane. Not just a coordinate plane, it's a Cartesian coordinate plane actually. The same Cartesian, of course. Same concept coming from the same person, French mathematician and philosopher Descartes. Now, whenever we have a Cartesian product, we can define a relation there. Any non-empty subset of a Cartesian product is called a relation. And whenever we have a relation, and whenever we have an ordered pair x, y in the relation, we're going to say x is related to y. So x is related to y means x, y is in that relation R, which is a subset of a Cartesian product. Too abstract? Okay, I agree. These examples will help you understand. Okay, let's consider the first example here. First relation is a relation defined by this equation here, x squared plus y squared is equal to 1. Do you recognize this equation from chapter 2? What is it? It's a circle centered at the origin with radius 1. And let's see, we have a couple of points here, x, y given by 1, 0, and that's this point here. And x, y is 1, 1, and that's this red point here. So this blue point is on the blue curve, as you can see. This red point is not on the blue curve. So 1, 0 is in the relation, 1, 1 is not in the relation. And you can easily check that. 1 squared plus 1 squared is equal to 1. That's yes. But, excuse me, it should be that. You see, 1, 0. So 1 squared plus 0 squared is equal to 1. Okay, that's yes. So this 1, 0 satisfies this equation, so it belongs to this R1, and as you can see, it's right here. But then again, what if we have this red point? 1 squared plus 1 squared is equal to 1. No, that's not true. As you can see, no. Now, what if we use the same terminologies that you studied here? If we do that, we can write it like this. X value 1 is y value 0, y value 0, but we can write like this. X value 1 is related to y value 0, 1 comma 0, but x value 1 is not related to y value 1, 1 comma 1 there. So the blue statement here corresponds to this blue point, and of course the blue statement there. And this red statement there corresponds to this red dot there. Now let's go to the next example. How about R2 given by x squared minus y squared is equal to 1? It's an hyperbola. So 1 comma 0 satisfies this relation here, and please check, the detail is left to the students. 0 comma 1 on the other hand, no. Please check this equation. And we can say like this. X value 1 is related to y value 0. Yes, 1 comma 0. It's on this blue curve. This blue dot is on the blue curve. But x value 0 is not related to y value 1. So 0 comma 1 right here, this red dot is not on the curve. Now in this kind of example, it is important to specify the coordinates here. If you forget about, let me copy and paste these and then write something relatively terrible here. So if you just throw away this x comma y and that x comma y, well, that's okay because they are paired, so I can clearly see which is x and which is y, and this point, that point. But then again, if you write like this, 1 is related to 0, but 0 is related to 1 like that, then it's really confusing because I did not specify the coordinate. Even worse, 1 and 0 are related, but 0 and 1 are not related. Oh, that's even worse. But this is bad enough. If you specify those coordinates, then there's no room for confusion. So please do it this way. Now how about the third example here? Turns out it's a parabola, and x comma y is 1 comma negative 1. That corresponds to this point here, and x comma y is 1 comma 2. That corresponds to this point here. So what can you say about this? X value negative 1 is related to y value 1. Can you say this? Okay. All right. Now here's the next question. Is there any other y value related to x value negative 1? When x is negative 1, yes, here's a crossing, and then we have this y equals to 1, all right. But is there any other y value? The answer is no. And this question and this answer are really important for a special relationship called function. We're going to come back to this question and answer later in subsection 1.5 when we deal with functions. So please remember that. For now, let's keep it at that, and then let's move on to the next topic that we have to prepare. Domain and range. Whenever we have a relation, we have a domain and range. Domain is basically the set of all allowed x-coordinate value. Range is the set of all allowed y-coordinate value. I'll be more precisely speaking, set of all x values, which is set of all x values that are related to at least one y value, set of all y values that are related to at least one x value. But if you write like these, that's a little bit confusing and difficult to understand. That's why I use the first term, all allowed, all valid x value, y value. Let's consider some example problems. The first example, R1, that's a circle. We studied those. Now, what is the domain and what is the range? Look at the graph and try to figure it out. Maybe you can stop the recording, stop this playback, and then just go through, and then you can check later. What do you think? X is going from -1 to +1. Y is going from -1 to +1 again. Like this. Not convinced? Okay, here are better visualizations. From -1 to +1, in that x-coordinate values, you can draw a bunch of vertical lines that share the same x-coordinate values. So for this x-coordinate value, x equals to 0.5, for example, we have this y-coordinate value is related, and that y-coordinate is also related. Here, I have only one y-coordinate value, 0. Over there, nothing. Same goes there, so we have only -1 to +1. Same goes to the range, except that this time we start from y value, -1 to +1, and then do horizontal lines. Each crossing point, that means this x-coordinate value is related to this y-coordinate value, 0.5, and so is this x-coordinate value. How about the next example here? Hyperbola. Well, let's see, how about the domain? Looks like over here, all's good because we have this curve. Over there, 1 to infinity, all good, we have this curve. But between -1 and +1, I have nothing here. So that's going to be out of domain. How about the range? It looks like okay, there's no gap as I move here to there. A bit difficult to see? Okay, alright. Here are a little bit better visualizations. -infinity to -1 and 1 to +infinity, we have these black, and then we can consider a bunch of vertical lines that share the same x-coordinate value. For example, this x-coordinate value is 2, and this crossing here and that crossing. So these two y-coordinate values are related to x-coordinate value of 2. But around here, no relation anywhere, no crossing. How about the range? Similar, but this time consider horizontal lines, and then select anything from -infinity to +infinity. We have to have a crossing, at least one crossing. So yeah, range is -infinity to infinity. Domain, that's a different story because we have this missing part here in the middle. How about the next problem here? Domain and range. Looks like horizontally can go anywhere, -infinity to +infinity. Vertically, however, it can go only up. So 0 to infinity. Indeed, anything here, and you can consider a bunch of vertical lines, and you can see those crossings. How about the range? From 0 to infinity only, and we have these crossings about horizontal lines, but down here we don't have any crossing, so these are invalid. So that's how we get this range, 0 to infinity. Okay, so much for domain and range. We're going to talk about functions, the precise definition of the functions in the next video. See you soon.